Yes, this presentation is about experimental validation of the evaluated measurement uncertainty. And I'll present first for you the agenda. First, a very short presentation of Eurofins Denmark, and then something about how we make method validation in my laboratory, including initial evaluation of the measurement uncertainty, about references and procedures, and the initial evaluation. And then to the subject, experimental validation of the evaluated measurement uncertainty, how we do. I will present references and procedures, and we use the top-down approach in our laboratory. And this means we have contributions from random errors within laboratory reproducibility, and we have contributions from systematic errors, the bias. Then we are always aware if we have to include contributions from other sources not included in the first place. Then we have to combine the standard uncertainties and we calculate the expanded uncertainty, and then a little bit about how we report the expanded uncertainty. So Eurofins is a big company. In Denmark we have 6 companies actually within Eurofins. And as said, I am in Eurofins environment. There can be slightly differences within the Eurofins companies how we calculate uncertainties, but I'll present, of course, primarily what we do in Eurofins environment. The references we use for the initial method validation and evaluation of measurement uncertainty is the Eurachem guide, the fitness for purpose of analytical methods. Then we have a Danish guide made within the Eurolab. This is actually based very much on the Eurachem guide. And then we have in our company an internal procedure how to make a method validation. The layout of the validation is a so-called standard layout, which is the minimum we do, and then sometimes we do more than that. But we have a control sample with known value in the low concentration area near LOQ. Then we have a high concentration sample in the middle or high range. We make as a minimum 16 replicates for both samples over 2 or more days. We collect all these data in Excel. We have a template we made internal in Eurofins, and we calculate parameters as LOD, LOQ, SW and ST, and RSD percent, and bias, and the uncertainty of bias, U bias, and the combined uncertainty and the expanded standard uncertainty in high level and at low level also. Often measurement uncertainty calculations is not considered as a part of the method validation itself, but we always do an initial evaluation as part of our validations. Then after the method validation, we have to follow the method. First, I'll show you the formulas we use for the calculations in the method validation. We have a very simple formulas for LOD and LOQ, 3 times within standard deviation and 10 times within standard deviation. And then the formula for the standard uncertainty for the bias component, and we have the relative expanded relative uncertainty and the absolute relative uncertainty in the low concentration area. This formula is from the Nordtest TR537, as I will show you in a moment. So the experimental validation of the evaluated measurement uncertainty. So after method validation, a method will typically go into use, daily use, and we follow this method with control samples. First, we'll talk about the references. We have the Eurachem guide here, quantifying uncertainty in analytical measurements, and specifically the Nordtest NTTR537. think many of you are already familiar with this guide, as it has been mentioned several times already in this webinar. So this is the basis for our calculations. We use the top-down approach. We use data from internal quality control. In every sequence we run 2 low control samples and 2 high control samples, and the results are plotted into X charts and R charts. And we have in the Excel template for the control charts, we have formulas for these calculations of the LOD, LOQ, within standard deviation and total standard deviation, RSD percent, the bias and the U bias. This is the UC, the combined standard uncertainty, and then the expanded standard uncertainty in the normal or high range, and the expanded standard uncertainty at low level. That means LOQ level. Yes. And then, as mentioned, we always try to be aware if we have to include contributions from other sources. So this is a control chart for a high control sample. This method is measuring phosphorus by ICP-OES after pressure digestion for a feed sample, the mixed feed for pigs. So this is an in-house control sample. And we see here the R chart showing the range for A and B replicate. And we have here the X chart showing the average on the day. And we have some calculations here in the bottom. And I'll show you more details what we calculate. So this control sample is a high control sample. The recovery here it was 102% rounded. That means that the bias is 1.9%. The S bias is the total standard deviation of the whole data series, so it is 5%, and we have 40 days. We have to include a contribution from the uncertainty of the reference material, which is often set at 2% by assumption, unless we have a better estimate. We sometimes have that, but unless we have that, we use 2%. The RSD percent is 5%. And we calculate the U bias. The formulas again are taken from the North Test TR 537. So I put in the numbers here, and we get 2.87% for the U bias component. It gives us an expanded. Sorry, we have to include then also the other part, the random part, and then we combine the uncertainties to get an expanded relative uncertainty at 11.5%, rounded to 12%. So that is the calculation for the high control sample. We have here the formulas taken from the TR 537. Yeah, this is a low control sample. It is corn, and we measure copper again by ICP-OES after pressure digestion. And the low control level of this sample is near the LOQ of the method. Again, we have in the bottom the calculations. And you see here, we have the formulas again. For the low control samples, we use absolute values for the components that is included here in the formula. So the true value is 1.8 milligram per kilo. The average is 2.05. So the bias is 0.285 in absolute values. So that gives us an S-bias at 0.728, and there's 37 data points. And we have the standard uncertainty for the reference material set to 5% by assumption. The total standard deviation for these 37 data point is 0.728 milligram per kilo. That gives us the bias, U-bias. With using this formula, we get a value of 0.322. And the expanded uncertainty then is just comes from multiplying this. Sorry, we have to combine first, of course, the two components of the giving contributions to the uncertainty, and we have the absolute uncertainty is expanded is 1.592 using this formula, and we round that to 2 milligram per kilo. Yes. So we also have calculations of the LOD and the LOQ, and these formulas we use for LOD and LOQ are very simple. There are lots of different approaches to calculating LOD and LOQ, but we have chosen this very simple approach to this. Is anything missing? That's the question that should always be asked when you are making evaluation of method uncertainty. Because with this top-down approach, it is definitely possible to miss some contributions. The control samples, are they certified or are they just in-house control samples? If they are in-house, the true value might be wrong, and the systematic errors, the bias might be wrongly estimated. Typically underestimated, but it can also be overestimated. Are the control samples more homogeneous than real customer samples? That's often control samples are very finely grounded, so very homogeneous. If they are more homogeneous than real samples, then random errors might be underestimated. And does the control samples undergo the total analysis, including all sample preparation steps? If not, the random, both random and systematic errors might be underestimated. Yeah, and then about uncertainty arising from sampling in the field. As many of you will know, the new version of 7025 says that labs shall include this uncertainty. In Denmark, we have a national local regulation that have other demands. This regulation tells us specifically not to include the uncertainty from sampling in the field. So we are lucky there. But it is an issue that is going to be discussed in the future about how to include sampling in the field. Yes. In these calculations I showed you before, we got the bias component from the control sample based on some kind of true value, and because it is an in-house control sample, it might be underestimated. So another approach to getting the bias component is to use data from proficiency testing. Of course, as a contract laboratory, we are participating in a lot of proficiency testings, and here we have for phosphorus by ICP OES after pressure digestion. We have a lot of different proficiency tests. Each column here is from one proficiency testing, and we have what we call here a trend curve. Points above this zero line, we have positive set scores, and the points below the zero line, we have a negative set scores. And as you can see here, we have a lot of negative and positive, and no systematic trend for this method. But we can use these data in the approach for calculating measurement uncertainty. We have here just some of these proficiency testings, but what we do is to calculate the bias for each of them. We have the nominal value and we have the measured value, and we calculate the difference in percent. And this is the bias for one proficiency test. And then we make a simple, we make the root mean square for this and get an estimate for the bias for all these proficiency testings. With this formula, again, these formulas are from the TR537 Nord test. So we combine the component from the proficiency testing with the component from the uncertainty on the reference values, combining them using this formula. And we have done this for phosphorus. The RMS is calculated as 5.47%, and the Eurofins is calculated to 3.21%. These are the formula we have used for this. And we again using the formula for calculating the overall uncertainty, now using the bias contribution from proficiency testing instead of the control sample. And we calculate the expanded measurement uncertainty here, and we see now we get 16%. Maybe you remember before we got 12% using the control sample. So the estimate of the uncertainty here is higher using data from proficiency testing. So what is correct? That is, of course, we have to evaluate that inside the laboratory. But this is just to show you that we use these two ways of calculating the uncertainty. Yes. Then a little bit about how we report the uncertainty. The standard measurement uncertainty is converted to expanded measurement uncertainty at 95% confidence level by multiplying by a factor of 2. We have an example here. We have a result of 20 milligram per kilo, and then the estimated uncertainty is 3 milligram per kilo, and the expanded uncertainty will then be 6 milligram per kilo. So we can report in different ways. Sorry, this should have been 6 and not 4. The result can be reported as 20 milligram per kilo, and the uncertainty 6 milligram per kilo, or it can be reported as 20 milligram, and the uncertainty is 30%. Yes, and in the last case, we report uncertainty near reporting limit. This is a copy of a certificate from our laboratory. Of course, I cannot show the customer, but it doesn't matter here. So here is a result, 2.46% of phosphorus. And we have an LOQ value and a method reference, and then we have the uncertainty here, 12%. And that is the expanded uncertainty on normal to high range. Yes. And the relative uncertainty is with a coverage factor of 2. Then we have a note on our report telling that for results near the detection limit or the quantification limit, the uncertainty might be higher than reported. As we have seen in many of the presentations already in this webinar, the uncertainty near the LOQ will be higher than in the normal measurement range. So it would be a very good thing to report the exact measurement or the calculated measurement uncertainty at the concentration level for the actual sample. This is a consideration we have for the future. At the moment, we have this comment on our reports, and then we report just the relative uncertainty in general. We might in the future decide to report the calculated uncertainty also in the low concentration range. one limitation is here of technical kind. You need to have an ELIM system which is applicable to do this. Yes, so this was the last slide of my presentations. So I'm ready to answer some questions if we have time.